It is time for the last talk. And those of us who are still here can enjoy listening to Mann.
Great, thank you. I thank all of your airlines for not putting you on a flight during my talk. As the last talk, I know Krista thanks the organizers yesterday, but Akia has been a very long time organizer. I think it's only right for someone else to call for us to thank so many organizers of this conference in the previous iteration. So it's been wonderful to be welcomed into this community. Okay, so this is the last iteration of my mini course. So it's going to be like the final exam where we use what we've done before and I test you that we try and use it to do something new. I thank Krishna for doing the review session yesterday about bifoliated planes. No, I'm kidding. But what we will do is I want to recall a theorem from last time that I stated, but said very little about how one proves this. That says if I have some non-trivial, I'll state it in the abstract formulation. I have some bifoliated planes, so I'll have two of them, so I'll call them PI 1 and 2. So that's just a topological plane with some pair of foliations. I'll denote them plus and minus, but you're thinking of them as maybe coming from stable unstable of an Anosov flow. And I want these to be non-trivial because back in, I don't know what it was, day one, we sort of discussed how trivial planes with these actions is an easy problem to sort of understand what flows they correspond to, and the theory is sort of known to sort of plot. So we're good on that case. So let's assume these are non-trivial, so they're not just product foliation R2s, and that they have some Anosov-like actions of a group. I don't assume the planes look topologically the same at all, or the actions are the same, but I just have the same group acting on these spaces. If the set of elements with fixed points is the same for each, then they're the same. So because of our weird motivation, or our original motivation, the weird notation for the set of elements with fixed points is this. So that's the set of G and G such that rho 1 P as a fixed point acts in the plane it's acting on. If this is the same set of elements for the two actions, then, well, not if, we can say if and only if actions are conjugate. Yeah, that's a great conjugate. By conjugacy that sends foliation to foliation. It might switch the plus minus ones when they're arbitrary labels, but it preserves the bifoliation. So that was our theorem. Oh, oops, there was a caveat, right? Which is that my planes have this weird thing you finally saw a picture of yesterday, thanks to Christian, which is if you have some freezer scallop regions, some extra data called a sign for each increment. Sign data for a tree of scallop. You can tell I want you to kind of ignore this hypothesis because we won't actually get to the technical part where it comes up, but we need it to be. Okay, and the motivation for this, right, was that it has as an immediate corollary translation between bifoliated planes and Anosov flows, is that transitive Anosov flows on a given compact free manifold, right, are determined or classified up to orbit equivalent, up to time change, by this periodic orbit data, right? That's where our notation for 6 points come from. They came from periodic orbit, 3 homotopic classes of periodic orbit. Okay, plus the ignorable hypothesis for now, which if you don't like, you can exclude by restricting the topology of this somewhat to ensure there's no reference. Okay, so my goal is to give you some hints on the level of things you can understand on the last day of a 2-week conference, at like what goes into the proof of this. But before I do this, I want to pose some questions. I'm very curious about what this set looks like for a flow. So you can kind of describe it explicitly for a suspension flow of a linear Anosov map of a course, for geodesic flow. Is there some general idea about, like how much of 3 homotopy classes, like the 3 homotopy classes of loops in your manifold, happen to be represented by periodic orbits? It's something that will kind of like grow exponentially, but like, is it some like, I don't know, large percentage of the fundamental group or not? I think that's like now, now this contains all the information, like what is it? It would be interesting to know if like a finite subset of this suffices. So could you do this not with like a topology on this whole thing, but like depending on your group or your manifold or something like this, there's finitely much data that could be. There's this kind of conjecture that I believe, for lack of reason not to believe it, that there on a fixed 3 manifold, there should be only finitely many orbit equivalent classes of Anosov flows. Maybe wrong, but I'll come down on the positive side of that conjecture just to feel it's better to be confident I'm wrong. And so that should say that there's some finite amount that determines it, but you could also try and weaken this by, suppose you just knew you had like containment of one or the other, right? As opposed to quality, one direction containment. You still get the same containment. This is done with this hypothesis for a special case of quasi-geodesic pseudo-Anosov flows on hyperbolic 3 manifolds and work with no perfect fits. This is a very special case. It's not, doesn't look anything like the case I wrote in John trying in work of Fenley and Kathryn, using a totally different library of techniques where you're using like the hyperbolic geometry a lot at the quasi-geodesic and 5. No perfect fits also essential. But they can do this with just containment. So that's just to say that there's lots still to be done. I also think it, I didn't rewrite all the axioms for what Anosov-like means. It's supposed to mean with some dynamical resemblance to the action that comes from an Anosov flow. But maybe, if that's the goal, you should certainly try and weaken our axioms and make like a nice result. Okay. That's meant to, say this is not the end of the story. But what is the story? So let me give you steps of the proof. Okay, so see, really, I want to give you some more theory about like how you work with these bifoliated planes. I think it's a beautiful object, make some kind of dynamics and topology. And to make you care, I'm going to frame it as like, well, maybe you care about flows and you want to prove this theorem when you have to. So let me state sort of some big steps and then we'll like, I don't know, sketch proof to the front of it. Okay, so here's maybe one I'll call lemma 1. Okay, which is in this setup, based on these hypotheses. So my assumption is I have two Anosov-like actions on different bifoliated planes. The first thing you want to show is that your first plane is Q, right? Is this particularly nice picture where your leaf spaces are house order, right? If and only if the second one is. In other words, you can kind of detect Q-ness versus not, or house order-ness of leaf spaces just from knowing this periodic set of elements with fixed points. I'll give some hints on how to actually do that later on, right? But that's obviously like a thing you need to do. Okay, I put this as one-on-one because it's early, and the proof really kind of bifurcates into a skew plane case and a non-skew case where, well, actually these are done in different proofs. They're so different. Let me talk about how the skew case goes. Let's try. How would you prove this theorem if both planes will have words or these six? Well, I need to define some kind of conjugacy, right, between these two actions, but the homeomorphism of the plane intertwines the two actions. I have a almost well-defined, almost good candidate here. I'm going to define a map between planes. Oops, it's only going to be defined on a dense subset. I have image dense subset, but it's going to be my candidate for conjugacy, and I want to show it like right. But on the dense subset, what's the dense subset? My dense subset is the set of points in my plane so that they are fixed by something. Okay, one of my axioms is this is a dense set. That was Anosov closing type behavior. Okay. So on my plane, these like colors for reasons. What does the set of fixed points of an element look like? If I fix this point here, okay, right, I fix the two leaves to it. So I fix the leaves that make perfect fit with this one. And I get another fixed point. And also I fix the leaves that make perfect fit with this one. So I end up with a fixed point. And this goes in both directions. So for a fixed G, its set of fixed points is like some ordered going up the strip. So this is. I'm using notation and forgetting my action, right? This is on P1, so I should say row 1. Okay. It looks like some ordered set going up like this. And I'm going to send this to, well, I know that row 2 of G has fixed points by assumption if row 1 of G does. So I'm going to send this discrete set to its discrete set of fixed points in an order preserving one. Okay, I have many choices of how to do this, right? Like I pick one to start with and I can send it to anyone, but after that I just want to. Okay. Here's the part of words. So the big claim, or all the words, is that there exists some coherent choice. So of my many choices for each one of these elements, I can kind of make a grid line for all of them. Okay. So that this resulting map, what did I call it? H. H is continuous. And hence it extends continuously to map between these two planes that spin vertical and horizontal, vertical and horizontal. I cooked it up that way on a dead set. So it extends to a map from, I'll write it P1 S plus 1, say I said foliation to foliation. So I mean, there's a unique continuous extension. Right. This is the entire, this is the hard work. It's not so much the coherent choice, but there's this that is easy word. And once you read it, it's not so hard to say that this is actually going to conjugate with that. Of course, maybe a step of that we already have, right? Which is if you do have a conjugacy between two actions, right? Like the fixed set of one element that is set to the fixed set of that element. And, you know, and if I apply some other thing, what the everyone's favorite equation, like that fixed of conjugate, and then I'm going to conjugate by that inverse equals the image of fixed G under F, right, is exactly the kind of thing you need to promote, knowing where fixed points of something goes to knowing how every element acts. Right? If I know that in a coherent way, like F inverse is fixed points and to F inverse is fixed points over there, telling me the action of F on the fixed set of G is how I do it. So that's a key point in saying conjugate actions. Of course, you need to do more work. That's why you do this. Okay, what do you do in the non-Q case? I want to naively do the same thing, like send fixed points to fixed points. But here's the whole problem, right? For a given G, the fixed set of row 1, I guess, like you get fixed an action on one thing, can be, it's like it's not some ordered thing. It can some discrete set, but it may be very complicated. Well, we know something about it, the final exam portion. But I studied how to solve the answer, right? This is a set of pointers of connected things right? So like that's one example, but like more generally, you could have something that looks like one of my positives. Pointers that are in the plane. These are ideal points that are at the boundary like that, right? But they might be adjacent to some other ones over here. It might be if I branch in all kinds of different directions, like a pointer to the side of the opposite. And you kind of like go off in all directions. You can use it on the side. So I'm getting this big set that's like not ordered. It's quite complicated. It has some kind of all over the place. To try and send that to something else, but like a priori doesn't even have the same cardinality. Like, what are you gonna do? Okay. Okay, but you can solve this problem by proving like fundamental lemma 2 that totally actually you don't even have to worry about. Here's lemma 2. If I have a non-Q plane with an Anosov-like always assumed also non-trivial, but here the trivial is then there's actually a dense set of points that are unique fixed points of alpha. So I can ignore all of these ones with multiple fixed points and just work with one. So there's a precise set of X such that there exists P, one of P, X. And actually, let me say something stronger than this is the fixed point. X is not a corner of any clauses. This is what I guess is to make this statement technically correct. What can you say? It's either a singleton or. So that was one of the things I raised my hand at last time. We weighed this extra axiom that said 6 more than 2 points, if you have some non-separated, 6 more than 1 point, 6 more than 1 point, there's like some more vendors connecting them, it's points for corners. That's inspired by and largely following work of Fenley. Okay, but that's not all that is. Many examples that are not corners of love. I think there's fact that the non-QPs is like in the trivial cases, we do everything. There are no law centers, there's not planes, so every 6 point looks like this. This is actually very well. Wait, let me give a name to this set. I don't know. I'll call it, I don't know, non-corner of any modular, not corner fixed point. So the non-corner. And in this case, say, I don't know, G is it has fixed points, so we do like this thing I really called here, but let's say periodic or whatever is not corner. Let me finish my outline, and then we'll prove this is fun. It's a fun thing. Okay, so erasing my theorem, you all remember my goal is to assume I have the same data, 6 point data, and build a conjugate. Given lemma 2 here in this non-skew case, what do we need to show? I can't do what I want yet. I need some other intermediate step. Lemma 3, this is what you'd hope was true if the actions were conjugate. Under my assumptions of the theorem, all right, what did I call these? Like elements with non-corner fixed points. Here, and I'm the worst at notation. These are the same for both axes. Let's prove they're conjugate. I've built a conjugate. That becomes the first step. All right, and now given this, I can do my naive strategy from before, but I don't even have to worry about like the many choices. I'm going to define my attempted conjugate being defined on a dense set. Then when I gave a name, M1 to N2, the non-corner fixed points of elements that's dense by lemma, by sending a point X fixed by row 1G, this unique fixed point, to the unique fixed point of how G acts on the other point. Well-definedness is now free. It goes from a dense subset to a dense subset. If there was a conjugacy, it exists, right? All right. So far, all of this works, even without this extra hypothesis on this nonsense. Okay, but now you have to work hard. You show this is a hard thing, right? Is that H is continuous as before and extends to conjugacy, except this is where the extra hypothesis comes in, except it may have exactly one kind of very special discontinuity that occurs on this tree of scallop region thing, and only one thing can go wrong. And that's the only place this hypothesis is. I should say that over the course of the proof, we use in many ways the circle compactification net infinity that Kathryn was talking about yesterday. I didn't have time to sort of import that into my mini course, but he mentioned very briefly this result that if you have two flows have the same kind of action at infinity, if and only if they're orbit equivalent, or two transitive flows, I guess, that can be proved using our result without the extra hypothesis, because we know here the only way this hypothesis goes wrong is like exactly extremely specific, and so you can work around it if you want to prove this. Not just something about these points, but actually, you know, you have the same action at infinity, you have. So that's just to say that, okay, this knowing exactly what goes wrong is helpful. Okay. So that's the outline, and but it being Friday, let's do the part. That's more fun. So what I'm going to do is I'm going to start by proving lemma 2. Giving you a taste for some of these ingredients. Q implies Q. We can remember that's something new. Okay, so lemma 2 live in the non-Q case. So look there, it's an assumption. And it looks okay. So this will be a good, it's an easier version of the arguments we did in this trichotomy lemma. So if that was like something you one day aim to understand, but the day has not yet come, today is a good warm up that I maybe should have done before. All right, so non-skew, I have a non-skew plane, implies that there exists some non-separated read by the trichotomy theorem, right? And by some consequence of, I think, what I was calling axiom 4, if you have non-separated leaves, then you have things in multiple fixed points, and there's like lozenges that connect them. There are some lozenges that share a side. Okay, so you look like this. I have some non-separated leaves, and you know, I have some other sequential leaves that limit onto these. Okay. Non-separated ones, let me draw them really big. So there's a sequence that limits onto here. They make a perfect fit here, and I'll use a different color. I see a picture that looks like this. So these are going off to infinity. Right. This also happens down here. I don't know what happens here. There might be some more lozenges, something, but I know as soon as I have some non-separated leaves, this picture occurs somewhere in my brain. So let's call these, I don't know, L1 and L2. The vertical, like which foliation do they come from? Yeah, oh yeah, sorry. Capital L is lozenge. Little L is gonna be, I'll try and keep consistent for you. I don't know if I should have used the R for rectangle or something, but anyway, that's it. L1. So I'm gonna find some open set inside of here where there's like no corners of any lozenges to be found. All right, how am I gonna take that open set? I'm gonna hit L2 with an element of my group that's acting nicely Anosov-like on this. So one of my axioms says that there's 6 points of elements are dense. So take someone who has a fixed point inside of L1 like that. Yeah, let's take it inside L2. All right. So I'm using a different color, but this should be like pink and orange, right? Sorry, pink and white. That's a leaf, one fixed leaf, and this is another fixed leaf, right? So up to, and this is fixed, say, by G, having this, and up to passing to switching G with its inverse, it contracts on the vertical foliation and expands on the horizontal. So let's try and draw a picture now of G of L2. So G takes this infinite leaf to another one further up. So it's going to go somewhere here. It at least has to cross all the way through L1. He's going to take this leaf to somewhere further down. And it can't escape out here, so it's going to have to go something like this. Maybe I should have done these in a color. Okay. And let's see, G expands these two other sides of the lozenge. So it's going to take this one somewhere, you know, out here. This will make some perfect fit out there. And this side, I'm supposed to expand it out there somewhere at a corner at a perfect fit down there. And it's do something like this. So outlined in blue is what G does. Or if, you know, as you apply higher powers, it'll get smaller, skinnier this way, and wider that way. All right, great. These are the ideal points, and those are the points. Okay, my claim is no point of L1 intersect the G of L2, that's some open set, is a corner of any lozenge. Okay, proof of claim. What's my target here? L1 intersects G of L2, this region. Pick a point in there, and I'm gonna just check. Okay, here's a point. So then at random. And I wanted to test, so to be a corner of something, right? You have your foliations I've drawn nicely here in vertical, horizontal, right? If this is a corner, it means I see perfect fits on these two sides and then some other thing connected. And so I have 4 quadrants to check. If I suspect it's a corner, it's going to be a corner in one of these 4 ways. And a way I can witness this, it's hard to go all the way to infinity and see what happens, right? But the lozenge is a trivially foliated region. So just inside here, I will see arbitrarily large quadrilaterals. Color-coded them as before. Their leaves alternate which sides, which foliations they come from. Arbitrarily long side length, because this is infinite. Okay, so let's just test this on the point that I drew here. And let's see, this horizontal leaf is sandwiched between these two blue ones, so it has to go at least that far. Okay. Let me try and pick a quadrant that doesn't have too much written in it already so I can test it. How about this bottom one? All right, so all work the same. So if I try to apply this test to this quadrant and see what happens, and I want to draw a rectangle, I'm supposed to be able to follow this leaf as far as I want, then turn a corner, okay, and I'll go somewhere. But similarly, also follow this leaf as long as I want, and then turn a corner. And these two things have to be able to connect up to make a nice rectangle. Okay, but I have problems, right? I have lots of problems. This red leaf needs to make it all the way over to where this white leaf is. But in between the two of them, I see a perfect fit. Right? This was color coded. That's white. That's red. This is infinity. This point is off my plane. No, this one is a corner. No, never mind. All right, never fear. That's actually easier to do with. This leaf separates this one from where I want to be, right? Cannot cross over here. I am stuck in this region. Okay. But this white leaf separates where I'm at from where I want to connect up, right? I cannot cross this region. And so you can never join these however you want in a rectangle. You're gonna just did I do this correctly? No, that one's fine. Sorry, these things are hard to draw when the board is figured in your face. What's getting me here is the perfect fit, actually. All right, let's do this slowly so that you can follow and I can follow. All right, so I'm trying to draw a large rectangle in between where I'm attempting to go places. This is the easiest witness. I see a perfect fit. So these both extend to infinity. There is no, however my plane goes, it ends here. There's no workaround. And this, I'm trying to use my white foliation to cross over to here, but I have this infinite half line that disconnects these two spaces, right? So this I can never unblock. I have to stay in this one. All right, and on this side of the perfect fit, well, actually I have worse than that. I have this half plane I was making an argument with before. I have to stay in this one too. So I can never connect the dots. I cannot close this up to a rectangle. Okay, exercise, copy my picture, take a picture, draw on your iPad or whatever, check every single quadrant. It's not hard, you just case by case find some leaves in the way of the square you want. Check each slide. Okay, these are some kinds of things to do on your own. Great. Okay, so now I found an open set where no points are corners. By my transitivity type axiom, there exists a dense orbit. I will find now an open dense set where no points are corners. And within that open dense set, I have a dense set of fixed points of elements. So I get a dense set of non-corner fixed. So transitivity axiom, which is, I think, was A3, implies exists that set of non-corner. So I told you that I can naively start to define a map. I'm gonna say very little about the students. That's a whole different secret. And maybe easier to read. So let's keep going on the next. And now I'm gonna give you the main ingredient, which basically no more proof, but we'll see the essential phenomenon. So here is a tool, P tool for lemma. What I call it? Well, actually, it's for all the other lemmas, including skew implies skew, and the idea of like extending continuously. Okay. And this is, how these weaves of fixed points interact. So the idea is that if I have, suppose I have some point that's like a non-pointer fixed point on my axis. And the idea is that I can use just knowing who has fixed points or not, and to set it out to detect how the leaves coming out of this point interact with the leaves coming out of other fixed points. For example, interact with leaves coming out of the image of this under some default. My action is also I would like to sort of test this. Or more generally, actually, before I say more generally, right? What is this? This happens to be a non-pointer fixed point. What age? What was this? This is 6 by D. The image of it under H is 6 by H. There's different things that can happen, right? Here's my X. Maybe after switching G with G inverse, maybe it's expanding that one to G. And it's conjugate. Okay, so here I hit this point with H. I see a different picture. I will HGH inverse, the conjugate will be expansive on the same foliation. You can contract it, it won't just opposite dynamics, it's literally conjugate, right? So this is my local picture for each. Let me label these. So this is the action of these. This is the action of the conjugate. Maybe I'll call this that. That's my local picture. And I have options for the global picture, right? Like this leaf may intersect that one or not. That can happen, or similarly, this leaf could intersect that one or not. Or I can have like one intersection but not both. I don't know. There is a representative picture, let's say we can intersect the those ones. Well, configurations that could happen. Okay, here's the statement of a lemma. So I need a name for this configuration. I'll call this configuration totally linked. So if this point is X and this point is Y, and I assume they are non-pointer fixed points of some G and F. And in fact, the only requirement I need is that they have conjugate dynamics. They span the same, locally conjugate dynamics. They span the same one. So I'm not allowed to replace this with like a one that contracts so that it's stiff. So the lemma is that, oh, sorry, I didn't put my definition, I just said it. I say X, Y, totally linked. Or maybe just TL. Whereas here, they're unlinked. Here you might call them particles. The point is that I can easily detect this configuration. So X, Y, non-corner, fixed point, and assume their L-bin has the same dynamic. So I take G F as in the picture. And foliation. Particular F with a conjugate of G that we define. With that setup, X and Y are totally linked if and only if one direction of this is for any power. If I do a power, a positive power, E and a positive power, this if I want something stronger on this side, I can say also, and it doesn't matter what we're going to do. This way, let's look what happens in this configuration. I can start all the leads. The space of leads that package this. If I apply a very big power of D, or any power, B positive power of D, it will shrink it down this way. The square with this interval with a B. I apply a power of X, it will contract itself this way. The interval of these goes into itself, so there's some fixed leaves in the middle, and on the fixed leaf there's a fixed point. And the work is to show that the converse of this is also true. And for that, I mean, the nice way to do that is to look at the dynamics on the physical energy. Depending on the configurations you have different contributions. Okay, great. So this gives you hope, maybe, that you can start detecting the topology of your plane, so the way the formations are arranged, just by knowing if that's in it or not. And we use this basically in various iterations, this kind of idea to reconstruct the bifoliated plane out of just like this set we had before. This idea maybe also optimistically helps you believe why that lemma 1 skew implies skew is true. Not quite the same setup, but in the skew plane, if you draw two things with fixed points, like they all have this like whole zigzag worth of fixed points, and everyone interacts with everyone. Whereas in a non-skew plane, I see non-separated leaves, and I can put, you know, a fixed point of one guy over here and someone over there, and they don't interact. You kind of start to do. Okay, so let me finish though by impressing you with our great skill of exploiting this kind of thing, right? You know, if my claim is true that I can reconstruct the way the plane looks just out of this data, I better be able to do things like detect when you're in a lozenge or not, or things like this. So let me just tell you some facts that are how you can rephrase what these foliations look like in terms of data you can. Right? And this is telling you, this board tells you that totally linking is data you can see on the periodic set. So if I can rephrase something in terms of like totally linking points or not, it's something you can recover from the assumptions in our the guide with fixed. Okay. So using i.e. totally linking non-corner fixed point. This is not to reconstruct foliation function. Here's something. In the proposition, I claim that you can rephrase whether you are inside the lozenge or not either. So, let's say, suppose I have some point that's where I want to define this H map or whatever. It's a non-pointer fixed point. So what is my action? And it's fixed by D. And maybe I have some lozenge fixed by another element. H, some lozenge, sorry, L, a lozenge with pointers fixed by so on. So that occurs in my plane. Here's my L. Okay. Can I tell if X is inside or outside of such a lozenge? I guess I can't tell right now which one, but here's the statement. There exists some lozenge with pointers fixed by H containing X, if and only if the following is true. So again, one version will be easy, one direction. If X lived in here, right, some fixed point of my element D, because my lozenge is invariant under H and it's a trivially foliated region on the inside, if I take a conjugate of G by H, well, right, it'll send X somewhere else inside the lozenge, and I will see this totally linked picture. H of X fixed by the conjugate of G by H. And these, this is what I just set up. These are totally linked. So if and only if X and H of X are totally linked. I just proved the easy direction for you. Okay, the other direction is okay, but this is true, and so you can see whether you're like in the chain of lozenges invariant by someone or you're out. Will not prove the right direction. It's hard. Instead, what's the good? Okay, here's the grand finale. I'm going to tell you that you can also detect, you know, maybe H fixes like a couple of lozenges, or like infinitely many. Who knows, right? And I have a criterion to tell you whether a point is inside this union or outside, right? But I could take 2 points on the inside and ask you, are they in the same lozenge or not? Right? Okay, we can rephrase this too. Oh boy. Okay, so this proposition says by unpacking all of this, just by knowing like who has 2 points or not, you can tell if 2 points are in the same lozenge or not. So what's my setup here? I can tell if you're in or out. So let's suppose that you have 2 points, X, Y, X, X prime. These are not corners. And they're in same. They're in some, possibly different. H is variant. Okay. Are they in the same lozenge or different ones? Same. Here's my detector. Let's draw a picture of what does happen if they were in the same. Okay, so I have some X and I have some X prime. the action of H on points of this, as I iterate H, things get pushed. The dynamics push things towards the corner and away in one direction. The dynamics of H are kind of going from this side to that side. That's not hypertension, or up to switching to its inverse. So if I take some iterates under H, I'm going to go off this way and off that way. If I consider some finite set of them, they all stay in this lozenge. And I can take a point over here, very close to the corner, that follows these sides for a long time. So we'll totally link every iterate. I can also find a point over on this corner. Okay, so it doesn't link this one, that's like over on the other side, so it's not going to interact with these sleeves I originally used. And also take it as close as I want to interact with any of these iterates. It's going to link any of these iterates. Call this one P, I'll call this one Q. This is how I remember it going in my mind. That's certainly a configuration that you can find where Q links all of these iterate points. What's the actual version? There exists some on corner. Remember, those are dense, so I can find one over there. So that P is totally linked with X. P is totally linked with X prime. Okay. There exists also some Q, like I drew, so that Q is not linked with P. But, oops, I picked finitely many iterates for all N. There exists a Q, but Q is totally linked with, what are my iterates? H to the N plus or minus both forwards and backwards times X and H plus or minus X. Turns out this is the if and only if that happens to be true that characterizes sameness versus difference. There's no easier thing with this time. Okay, this is meant to impress you, to tell you that you can reconstruct a plane, but it gets increasingly more difficult to phrase topological words like, foliation phenomena. Are you on the same side of a leaf or not, or whatever? In terms of something you translate into this, people need to do it. Yeah. And that's how you arrive at our result. Thanks.
Well, are there any questions? People who want to know more about how to reconstruct planes? Right, so I'm not sure if I could reconstruct a plane. Well, I'm convinced that you can do it. So let's thank Katie again. Okay, I want to say a few words. I want to